Okay, thank you, Ellis, and everyone for having me here. So I'll pick up with the material that Leo was just telling us about, with some possible extensions, musings, speculation, wild, crazy thoughts, and some mostly open problems related to how far we can push the techniques and the ideas that Leo just told you about. So just to recall where we left off last, and please interact a lot. So ask a lot of questions. I have enough material to either go dramatically under time or dramatically over time, and we can make that decision at there'll be a mark at which we.
7 slides.
Yeah, exactly. Yeah, and one of them is the cover slide. Yeah. All right. So. To recall the problem that Leo was talking about and that we were interested in solving, it's a short generator of a principal ideal problem, and I will call it SGPIP. There'll be several acronyms in the talk, but I promise computer scientists may have their names initialed, but all mathematicians I've written out their full name. So I hope that makes everybody happy. Okay. Yes, sorry. That's just how it came out. Okay. All right. So the problem is we're given an integer basis, a z basis, of some principal ideal I in a ring, a number ring R, and I is promised to be principal, and moreover, it has a generator G, which is rather short, and that's in quotes. And the goal is to find this original G up to your trivial symmetries. Like multiplication by roots of unity. Okay, so the theorem that Leo told you about. Yes, please. Yes. Yes. Yeah. Okay, so it's the same notion of rather short that Leo was talking about. So basically, we want all the embeddings of G to be roughly the same size. Okay, so their logarithms are rather basically the same, so that puts you inside the fundamental domain. But yeah, more right. It's not an absolute size because you could just triple G or multiply it by 1 billion, right? And you just made it 1 billion times longer. So it's more about how short is it relative to the norm of the ideal or the sparsity of the ideal. And so it's deliberately somewhat vague here because depending on what your application is, it may be slightly different. And I will be more precise in like 2 slides.
One thing to point out, what you're asking, it's not the norm. Scaling really have no effect here.
Yeah.
Always compute the norm of the ideal, scale it back to the norm. The scaling is not.
Yeah. It's rather short relative to the net density of I, density of the norm of the ideal. So yeah, the theorem Leo told you about is in at least in prime power cyclotomic rings R having degree n over the integers. This SGPIP problem is solvable in classical sub-exponential time and quantum polynomial time. And he told you about the second step of how this theorem is proved. So there's an algorithm here. The algorithm to solve SGPIP is the composition of SGG and GPIP. The G's annihilate each other, and you have to put SGPIP. So start. Yes, I'll define them right here. So this problem here, GPIP, is find some generator of a principal ideal given that principal ideal, given a representation of that principal ideal. So this is find a generator of a principal ideal problem. And then the SGG problem, which I'm just making up, is find the promised short generator of the ideal given some arbitrary generator of the ideal. So if you compose these 2 steps, you see that they give you the promised short generator of the principal ideal. Right, I had an asterisk there, and then the paper came out yesterday.
Okay.
So there is a paper that makes this claim for what? For, is there some heuristic there? I see. Okay, so I'll just put a little. Yes, so this is all the attributions from Leo's talk. There are no new, this is just where we left off. That would be bias and song. 15. It's a tech report on the U Waterloo site. That's bias and Peikert, I think. I'm not sure. Yeah, nothing disappears. If you put something on the internet, it never goes away. Yeah. Listed as withdrawn, yeah. So if it's withdrawn, I guess if anything listed as withdrawn would not be reliable, I guess. But so this is just recapping Leo's talk and what the pieces of the puzzle were. All right, so just to give a bit more context, and Leo already talked about this a little bit, but some context for what this means for crypto based on rings and ideal lattices and things like that. So as you already mentioned, a few of these initial works are, well, they'll be classically weakened and quantumly broken by this attack. So these works on multilinear maps, for example, and one of the simplifications of fully homomorphic encryption. It turns out that if you want to break these schemes, you don't actually necessarily have to solve the SGP IP problem. All you have to do is solve what I'll call shortest vector problem in a principal ideal that is guaranteed to have a short vector, a short generator. Excuse me. So you don't necessarily have to find the short generator, you just have to find a relatively short vector in the ideal, and that's enough to break these schemes. And certainly finding the short generator is a short vector in that ideal. Okay, so this is a reduction saying that if you can solve PIP, you can certainly solve SVP on these particular ideals. So that's somewhat bad news for security for these systems. But fortunately, the story is mostly okay still. So most ring-based crypto is not really affected by the attack as far as we can tell. And it's basically because the security of the schemes is based on or lower bounded by harder or more general problems. So here's a long string of acronyms. I will say what they all are. So again, this is find a short vector in a principal ideal with the promise that there exists a short generator. And this is the more general problem of find a short vector in a principal ideal, and just any principal ideal. And such principal ideals may not have short generators in them. In fact, we'll see that this promise, the short generator promise, is actually quite a strong special property. Okay, so this is the problem of find a short vector in any principal ideal. And so far, we don't have an attack against this problem, despite the techniques we've seen so far. So we don't have an attack on this problem. This is the problem of find a short vector in an arbitrary ideal, regardless of whether it's principal or not. So that's even more general. We don't have an attack on that. And then as we have heard a little bit about the problem ring SIS and ring LWE problems, these are at least as hard as this problem here on SIS. So short integer solution and learning with errors over rings. So these problems are at least as hard as finding approximately shortest vectors in arbitrary ideals via quantum reduction in the LWE case. That is true in any fixed number field, yes. So in particular in cyclotomics. And then most of the crypto, or a large fraction of crypto that you'll see out there, is based on, for example, this problem here. So it is lower bounded via this sequence of, well, these are all trivial reductions. This one's somewhat less trivial, but lower bounded by problems which still we don't know how to break yet. And likewise, NTRU, which we'll talk about a little bit later, also lies somewhere above this danger zone here. Although I couldn't quite find a formal reduction that I could state definitely, but so far we don't know how to break Andrew using, by breaking this problem. Okay, so so that's good news for crypto security. And if there's a main message to take away from here, the attack, as you can see, when we go from red to green, the attack technique very crucially relies on this promise or the existence of this unusually short generator of the principal ideal. Okay. And we'll see that, well, we already sort of saw it in Leo's talk, but we'll see it a little more here. So the motivating or animating question for the talk today is, well, how far can we push the techniques that we've seen that we saw in Leo's talk? So there are many directions you might imagine pushing these attack techniques to try to make them apply more generally to other scenarios. So the agenda is first to discuss the relative rarity of principal ideals that have these short generators. Okay, so these turn out to be quite unusual ideals, and that seems to be the property that is making the attack work very effectively. So we'll talk about that a little bit. And then we'll talk about some ideas for how you might extend this attack on the short generator of a principal ideal problem to non-cyclotomic nanofields. So that started to be discussed at the end of the previous talk, and we can pick that back up. And then we'll have a decision of whether we want to eat lunch or listen to another half hour of talking. And then we can discuss some potential ideas for how you might or might not be able to apply SGPIP to attack the more commonly used problems in crypto like N-true and NFT. So any questions about where we'll go? Let's go there. Okay, so here are a couple of facts. You could even call them theorems if you put quote marks around them, maybe, on how rare it is to have a principal ideal with a short generator. So there are two facts here, sort of two sides of the same coin. So the first says what fraction of principal ideals, and this is all in cyclotomic rings here, what fraction of principal ideals actually have a generator G whose length is nearly the shortest, so nearly the minimum distance of the ideal. Okay, so this says the generator G, its Euclidean norm under the canonical embedding is a small factor worse, within a small factor of the minimum distance. Okay? And it turns out that a very, very small fraction, so like an n to the minus n fraction of ideals have this property. Yeah, so I've been pretty deliberately vague about what it means fraction of ideals. But one thing we can do, and this is what the argument will do. So take all principal ideals and then just scale them down to have a norm 1. So they become fractional or even irrational ideals. And so we take all principal ideals and scale them down, normalize to have norm 1. Then you can talk about a uniformly random such ideal. Okay, there's a notion, a way to give a probability measure on those, and then the probability of an ideal having this property would be roughly infinite. Yes. Sure. I mean, you probably do lots of different approximations. You really take all ideals of norm, I don't know, less than 2 to the n squared or something, and restrict the principal ideals, and you'll get roughly the same kind of behavior. So under, I think, any reasonable notion of a random principal ideal. Yes, yes, exactly. So, and then the other side of this coin is that, okay, so what if I took one of these typical or random principal ideals, then what would its shortest generator look like? How would its shortest generator compare to the minimum distance? And typically it will be quite bad. It'll be at least a 2 to the root n factor larger than the minimum distance. Could be even bigger, but the very simple naive argument that I'll show you gives you at least this kind of bound. So the upshot of this is that if you look at, if you want to think about finding short vectors in principal ideals, arbitrary principal ideals, then typically finding the shortest generator doesn't do very well in that. Because the shortest generator is typically very, very much worse than the shortest vector. Okay, so it's something kind of interesting. It illustrates the unusual nature of these ideals that have short generators.
It is actually hard.
Is it? Yeah.
Essentially, if you take a typical idea, you do have generators.
We might be able to see it from the argument. Yeah. I'm not sure, but we'll see. This is all for cyclotomics. Everything's here for cyclotomics. So again, as I mentioned, so for simplicity, let's normalize the ideal. So we'll scale it down to have norm 1, so it becomes a fractional or even irrational ideal. And what you can prove elementary bounds, when the norm is 1, then the minimum distance is between root n and n in the cyclotomic field of degree n. And so let's just say, say we have our ideal I here, and we just look at the set of all generators of the ideal. So this is in fact, take an arbitrary generator G and then times any units, right? This is exactly the set of generators in of the ideal. And so if we apply this log embedding, we take logs on both sides, then we get the log of the set of generators is just the log of G plus the log unit lattice, so the log of the units. So what we have is a coset of the log unit lattice. Some shift of it by log G. And so now we can ask, okay, well, if we want to require that there's a vector, a generator G of this norm bounded by this norm here, then what we see is that if you want the Euclidean norm of G to be, say, polynomial in n, then what you need is for every one of the embeddings of G, you need the logarithm of all of its embeddings to be some c times log n, where c is the same constant as appearing in the exponent. Right? So we need log of all these embeddings to be order log n, and therefore the L1 norm of log G will be n log n. Everything okay so far? Too simple? Maybe? And all right, so now we can ask, okay, what's the volume of the set of such G's, such little G's? Yes?
Can you explain this thing in
Yes.
log of the absolute value?
Right, so I should, let me be more explicit about this point here. So if you want all so this is the Euclidean norm of G, so it's the sum of the squares of the embeddings of G, square root. And so if any of the embeddings exceed e to the c log n, then one of these embeddings is already larger than poly n. And then so the Euclidean norm is obviously larger than poly n. So you need all these embeddings to be themselves smaller than poly n, and so their logs have to be order log n. Yeah, the L1 norm is similar to values. Yeah. Yeah, the absolute value of the log is always positive. Yes, yes. Oh, okay. You want me to say that yes. Yes. The sum of the logs here is 0. Sum of the logs here is 0. That's right. Yeah. So because the norm of G is 1. So okay. So we know that this L1 norm is order n log n, and now we can just ask, well, what's the volume of such G's? Right? So the volume of such G's, you can just look up. the volume of the L1 ball of a particular radius is 2 to the n over n factorial times the radius power n. And so you just do a little calculation, and you end up with, this is order log n raised to the n power. And we also know that the volume of the log unit lattice, we actually know this pretty well asymptotically at least. It's called the regulator, and it is theta, so some constant root n, all raised to the n power. So I didn't draw the nice pictures that Leo did, but if you just imagine that this is your log unit lattice, like so. Then the G's, we can call this the origin here. So the G's, which are good in this sense here, all lie in this L1 ball here, okay, around the origin. Okay, and then if we take the coset of these G's plus the log unit lattice, we just get the same thing around all the lattice points. So the volume of this area, this region, is only log n to the n, whereas the determinant of this lattice, okay, the volume of any fundamental region, this volume is square root n to the n. Okay, and so the ratio of the good G's, so the short G's, to all a random G here is very small. It's only, so the ratio is at least it's well, log n over root n to the n. So that's vanishingly small. So everything makes sense here? Okay. So essentially picking a random principal ideal corresponds to picking a uniformly random coset of this log unit lattice, and only those cosets which lie inside these regions are those that have short Jack numbers. So that basically proves number one. And then for number two, you can basically ask the question, well, if a typical or random choice of a coset here, how large do we have to make these balls before we cover the whole space? Basically, we have to answer the question, and what that means is you need to allow your bound here to grow to something like n square root n. So, right? So these log of sigma g's will have to be as large as around square root n. And so when you then take the exponential, you get something like 2 to the root n as your Euclidean norm for G. That makes some sense? Okay, so that was agenda item 1. Any questions about this here? Yeah. Mm-hmm. Right. Yes, I think, well, you have to take some care about that because if you take a random ideal, then you're getting a random coset. A random principal ideal gives you a random coset of this log unit lattice. And then when you decode that, are you solving CVP exactly? Maybe not, right? You're getting some, okay. Okay, just using decoding? Yes, right. So then just using the decoding basis, you're sort of interested in the L infinity norm of the error vector there, and then it's 2 to that L infinity norm is basically the norm of your general. Probably it's either square root of n or n. I'm not sure. You have to be careful with the L infinity norm and look exactly at the basis vectors. Yes, they're all in log space. Well, so I've done the scaling here. So I'm not restricting G's to be integers. I'm saying take the number field and tensor it with the reals. It's the only way to really make this rigorous. But yes. So G's here are not integers. But if you yes. Yeah, so at some point, if you put a norm bound on G and you make it large enough, and you choose uniformly among those, heuristically this behaves more or less the same way.
Assuming too is the time.
Yes.
You get something non-trivial by finding.
Right, right. You get something better than LLL gives you, for example.
Right.
It is. Yes, exactly. So we have to check carefully about Leo's question, right? Is whether I've done the calculation many times, and each time it comes out to be something different. But it's always either square root n or n. So one of these is I think you vote square root n. Great. I mean that would be pretty interesting and non-trivial. Sure, sure. We're among friends. A lot of factors. Okay, so you know it would be interesting to do a similar analysis for non-cyclotomic number fields here. I think there's nothing too much that you need. We're only using the volume, so we're only using the regulator of the units, and you can get that from class number formulas and things like that. So you should be able to repeat this analysis for other interesting cases. Maybe. I hope. Okay, so let's then go to the questions, some of the questions that came up toward the end, which is, so back to this short generator of a principal ideal problem beyond cyclotomic number fields. So if you recall the high-level strategy of the algorithm that we saw, it's that to recover a promised short generator, so we know short generator exists, and to recover it from any generator of the ideal I, it suffices to have some good enough basis of the log unit lattice, log R star. And it need not even be a basis. It's good enough if it generates a dense enough sublattice of log R star. So we actually used the fact that we might not have an exact basis, but the index was conjectured to be very small. So that was good enough for us. Okay, so to do this, you know, for cyclotomics, we use the standard basis of the cyclotomic units. But you can ask the question, should ask the question, can we get such a basis for other number rings? And I think people have already asked this question. So here's a general answer. If my number field and my number ring is completely arbitrary, and it's just given to me, then I can pre-process it for a while. So this is before I know the ideal. So let's suppose we're in a world, and this is the typical crypto world, at least for constructions that we usually consider. There's a ring which is sort of fixed for everybody in the world, and then they generate their own keys, you know, whatever the ideal or whatever it happens to be, they generate their own key relative to that fixed ring. So if this ring is used by everybody in the world, then we can pre-process it for a while. So we can spend a lot of time to first find the unit group, right? Find the generators of the units, and then moreover improve those generators to be short using, for example, a shortest vector algorithm like Oded will show us after lunch. So this will take roughly 2 to the rank of the log unit lattice time. Yeah. Which part of? Oh, so finding the unit group will be sub-exponential typically, but then making it a good basis would typically, in general, would be the slowest part because it's exponential in the rank of the lattice. Was there a question? This is for? Yes, yes. So this is what we're doing here is considering the second stage of the argument, right, which is to convert any generator to the short generator, right? And so what I'm suggesting here is we can pre-process this ring to find a good basis for the log unit lattice of the ring. And then once we have that good basis, things become a lot better after that, because then we can, well, relatively quickly solve many instances. Like someone generates a key, we solve it. Someone else generates a key, we solve it using this preprocessed information. And the reason why this is relatively more quick is because we just have to solve the PIP problem, which is sub-exponential, and then we convert the bad generator it gives us to a short generator, and that's very quick once you've got this good basis. Okay. So I'm probably hiding a lot of details, like does it actually work? Does it give you a correct answer? And that depends on how good the geometry of your basis of log R star is. Will quantum algorithms help here? They would help with the PIP part, right? Because so they'll help with finding the units. That would be polynomial time, quantum polynomial time. And but they won't help for finding the good basis of the unit, as far as we know, right? So yeah, whether or not it's quantum, this is still the bottleneck, it seems. And but if you had quantum, then this solving instances becomes quite fast, because the PIP would be quantum. Well, I don't know that it's general enough. The algorithm is general enough yet, but assuming you had a fast quantum PIP algorithm, then you're in very good shape. Okay, so this is some costly preprocessing one time, and then you can break everybody's keys if they all are ideals with short generators. Okay, so this is the most sort of general answer you can give, or an answer you can give for the general case. But typically in crypto, as I was saying, the ring is somehow fixed usually, and special in some way. It's not like some arbitrary number field, number ring. Usually we fix some rings that we like and then work in those. So in such particular cases, you can indeed do better or even much better. So this is just one example I found. I found it in Conrad's notes, actually. But for example, take a multi-quadratic. So adjoin several square roots of d1 through dk. The d should be square-free and multiplicatively independent modulo squares. And here are two nice facts about this number field. So the first is that the unit rank, so the rank of the log unit lattice, is 2 to the k minus 1. And the d's are positive. Oh, yes, thank you. Yeah, that's the other appropriate. Thank you. Yes, positive, non-square, and multiplicatively independent modulo squares. Okay, thank you. Yes, it's very important. Okay, good. So the unit rank of this, because there are 2 to the k real embeddings of this number field, then Dirichlet unit theorem tells you that the rank of the unit lattice is 2 to the k minus 1. Now, by some coincidence, this is also the number of quadratic subfields of K. And these quadratic subfields are precisely Q adjoin square root D sub I, okay, where I is an index set, a subset of 1 through K, non-empty subset of 1 through K. Okay? And D sub I is just the product of the D little i's over that index set. So they're exactly the 2 to the K minus 1 quadratic subfields. That is exactly the unit rank. And, well, if you have this quadratic, for any quadratic subfield, you can pretty quickly compute the fundamental unit of it. So this is a real quadratic subfield, so its unit rank is 1, and you can relatively quickly find that fundamental unit as long as its D is not very big. So I'm thinking, okay, I just answered. Okay. So it won't be very big because, so think of these just for concreteness, 2, 3, 5, 7, right? And the dimension I'm wanting to be in the hundreds or thousands, right, in order for this to be cryptographically relevant. So even the product of log many primes is not very big. So I think this is all pretty small in terms of, I think the algorithms laugh at this, at how easy it is to do, maybe. We'll see. So, yeah. I want 2 to the k to be small. It's n. 2 to the k is my n here. No, the first log n primes. Yeah. Yeah. So it's pretty small. So, well, one can, in some amount of time, which is not totally prohibitive, compute the fundamental unit of all of these. Okay. And now the natural question is, okay, great. I've got these 2 to the k minus 1 fundamental units for each of these quadratic subfields. And oh, my unit rank of the original is exactly that 2 to the k minus 1. What happens if I put all these units together? And guess what? Well, they may not give you a basis for the unit group of k, but it's known that they give you a finite index subgroup. A power of 2 finite index? Great. Okay, even better. So you can find a proof of this in Conrad's notes on the Dirichlet unit theorem. Keith Conrad, yes. Great notes on this topic and much more fun stuff in there. So somewhere toward the back of these notes, it's like a 2-paragraph proof. And it's very quick, clean, elementary. So what we get is a way of computing in a relatively small amount of time a finite index group of set of generators for finite index subgroup of the full unit group. Okay, so that's something. I mean, we've just computed the unit group representation of the unit group. The question is, how good are these units geometrically? So I mean this now in the log embedding. Are they short? Are they orthogonal? Is their dual good? Right? Are they Gram-Schmidt vectors? You can ask all these nice geometric questions. They should all be relatively straightforward to answer. You know, if you ask Sage, plug it into a. Maybe. Yeah. Yeah. So if they're basically orthogonal, we're in great shape as long as they're not too small. So there's good reason to be optimistic. I haven't done the experiments, but yeah. Good. So that's good news for the attack. If indeed these units are nice and nearly orthogonal. And then the other question is, how small is this finite index? So it's a power of 2 apparently. If it's not too bad, it's not too large. Okay. Is this square enough to do it? Or? Power of 2? And to the n over 2, where n is 2 to the k. Okay, so that's too large. Yeah, that's a lot. That's a lot of there. Yeah. Okay. Okay, so this might be good. The answer, we might like it for the attack, but this might be something that has to be overcome. Yeah, they're so it's easy to do experiments here, right? Just yeah. Right. So try a lot of these, you know, put it into Sage. I think all of this can be checked experimentally quite easily. Yeah. Great. Okay, so these are, you know, open. I hesitate to even call them open problems. But, yes, it's to understand, right? It's to understand, like, so. Right, so you can try it in low degrees first, right? I mean, to get the right answer, you need to know the full unit group. Right, right. But it will do it. Right, right. But the question is, how quickly can Sage compute the full unit group of K? For degree 16 or so, it'll give you an answer relatively quickly, I think. Right? Well, in some experience. Yeah. Okay, yeah. Yes, okay. Quickly patch it up. Sure. Okay. Right. Okay. Okay, so yeah, so there's a lot of cool yeah. To the K here? Okay. So do we? So a possible approach here might be to first take the subgroup that you get via this pretty easy thing, and then try to patch it up to get the full group. Okay. Okay. Good. So I mean, this is just one particular case I stumbled across, but the more general question is, are there other somewhat nice number fields that would make sense, or you might think might make sense for crypto, for which you can sort of either analytically or computationally or both come up with a good basis of the log unit lattice? That's the overarching question. So, oh, here's one more example. I think Jeff suggested or mentioned this here, and also Dan Bernstein has suggested this ring here, where you take Cx mod x to the p minus x minus 1. P is a prime here. And, well, you can just write down a handful of units for this ring. So for example, x is a unit. The dth cyclotomic in x for d dividing p minus 1 is a unit. That just comes from the equality x to the p minus x equals 1, which is a unit. And then you factor x to the p minus x into this and all of these. So these are all units. They're not all multiplicatively independent, but if you take several of them, oftentimes they are, and oftentimes they look geometrically pretty good. It's far from a full generating set for the unit group, but it's a start. Let's give you something. So there's plenty of number fields you can play with to try to investigate this question. Questions about this one here? Oh, okay. So my time is officially up, but except that we don't get lunch till 12:30. So I can keep going and talk about the third thing, or if you feel like enjoying the sunshine. It's too hot. Okay, so yeah, she knows. So in recognition that there are absolutely no theorems beyond this point, or allowed beyond this point, if you squint, you might see a lemma or two, but even that. Exactly. So in recognition of that, I was going to do things on the board from now on, right? Okay. We'll make do it in the math style here. So feel free to leave if you like, or you can. Okay, good. Okay. So the motivating question here is this visible? Can we? Okay, so other problems from ring-based lattice cryptography. So for example, NTRU. Right, this is so NTRU is the crypto system and associated problems introduced by Hofstein, Pfeiffer, and Silverman in 96 or so, and 1996, 1896. Okay, so here's the very briefest description of NTRU possible. So our secret key will be some short F and G in the ring R. So as usual, our ring will be cyclotomic n power 2. For example, this is a common choice. And so by short, I mean, so they may have ternary coefficients in 0, plus minus 1, something like this. Okay, or you could take them to be larger if you like, for more security. Okay, and your public key here is merely some h. H is G times F inverse mod Q. Okay, so note F has to be invertible modulo Q here. That's an additional constraint on the secret key. Good. So but that's easy to obtain. So I won't even show you the encryption and decryption algorithms. You can look them up in any number of sources. But what we'll be concerned with is the problem of recovering the secret key from the public key. So relatively clear so far. So our baseline attack is just a brute force search for F. Okay, so you can try all 3 to the n ternary polynomials, for example, and then when you get the correct one, what you do, well, for each one of them, you try to just check that H times your candidate F. Okay, this F tilde mod Q is. Okay, and when you find the proper F, well, notice that H times F equals G. G itself is short. And so when you've got the correct F, you get back the correct G. Yes, it could be. Think of Q as in the low hundreds to thousands. And it need not be prime, but it's a common choice. Q will play almost no role in anything that you do. Okay, so we just check that H times your candidate F is short. And when you've got the right F, up to obvious asymmetries, obvious equivalences, you get the correct G. Okay, so questions about this? So this is just 3 to the n time. Pretty slow. There are lattice attacks, which are faster. Which are better than this. But what you have to do is phrase the problem as a lattice problem. So let's do that now. Entry lattice. So we'll call it L sub H. So this is a lattice associated with the public key. And this is just the set of all pairs UV in the ring, both in R. such that U times H equals V modulo Q. Okay, so we can verify a couple of simple things. Fg is in this lattice, right? Because F times H equals G modulo Q. And let's see, what else? As is times X, G times X, and so forth. Okay, so you can multiply both entries here by any polynomial you like. And so therefore, LH is an R module in R squared. Okay, a rank 2 R module. Rank 2 R module, so an example basis are the two, are the pairs 1, comma H and 0, comma Q. Okay, so we just verify that, well, 1 times H equals H mod Q. Don't even need the mod Q. And then 0 times H equals Q mod Q. These, and in fact, this is a full basis for that. Okay, so that's all basic background on this thing. Let's just notice. So remark is that, well, this lattice LH, it contains this short vector, right? F and G are both short. So this is a short vector and in the lattice, but given this is like the public basis, you can get it from all the public information. Neither of these vectors are particularly short. And if you do lattice basis reduction hard enough and long enough, eventually this vector will pop out. It will take a while. And so when this vector pops out, you have learned the secret key. Let's see. Okay, but remark is that LH is not an ideal in R. Right? It doesn't even live in R, nor in the product ring. It's not in. It's also not an ideal in the product ring R squared. And so it lives in R squared, but it's not an ideal in that product ring, simply because, well, it's an R module. You have to multiply both of the coordinates by the same thing. You can't multiply them by different things and expect to stay. I didn't, but someone else did. Okay, so that's what I want to discuss. No, it does. It does. Well, sort of. Okay, so what I'll discuss is earlier, I guess in the spring, Dan Bernstein had an idea to do precisely this kind of thing, put a different ring structure on R squared, and try to apply a short generator of a PIP problem to try to attack this and get FG out. Okay, so this is a proposal, and I'll tell you about the proposal, and then what I see as some of the obstacles that it has to overcome to make it worthwhile. So let's see. So is Dan a computer scientist or a mathematician? Okay, well, he'll be a mathematician. All right, so Bernstein 15 suggests an approach to so to attack this entry problem using, say, an oracle for SGPIP or algorithm for SGPIP, whichever. Okay. And so let me give you the first high-level idea. So the main idea, in a very small nutshell, is, as Henrik said, to put sort of a different ring structure on R squared, essentially. Okay, or in another way, to make this lattice L sub H into almost a principal ideal in some other ring, so in a certain quadratic extension S on R. Okay, so we'll define a new ring S, which is a quadratic extension of R, and we'll want L sub H. Well, it won't become a principal ideal in this particular ring extension, but it'll be maybe close to 1, and then we'll see what we can do. So, okay, that's the basic idea of this. All right, so what should we do next? All right, so the basic idea is to sort of replace this H in some sense with a variable instead. So introduce a new variable. So technically what we're going to do is, so let's let R belong to the ring R here, be, let's say, as small as possible. And let's say that R will be congruent to H squared modulo Q. So what we can do is square H and then take its sort of minimal representative, right, at some basis of R, and just push it to be as small as we can make it. So R's coefficients will be between minus Q over 2 and Q over 2, for example. And they'll roughly be random in that interval. Okay. So as a polynomial in X, that's what R sort of looks like. This is not the only thing you can do. So for example, or well, let me just say, so we'll let S be the ring R adjoin square root R. Okay, or equivalently, call it R adjoin Y, where the minimal polynomial of Y is Y squared minus R. Okay. More generally, this isn't the only thing you can do, but in the same spirit, we could say take Y to have minimal polynomial, say S Y squared minus R, something like this, or even T Y squared minus SY minus R. Okay, the point being that SR should be as short as possible, or T SR. Okay, all these should be as short as possible. So this is the first most naive way of doing that, just by taking R to be a minimal representative. And you probably do slightly better here, although maybe not appreciably better, because you have to use some lattice reduction or something to get these down below the range of Q. Okay, so we'll just stick with this one for simplicity and leave the generalization to the reader. Okay, so let's see what we can do to change. There we go. I'll leave those. Let's see if we can push or mangle this L sub H to look like a principal ideal, or get it as close as possible to 1. So the basic correspondence is we'll map whatever we had in R squared before, we'll now treat it in S using the following map. So the pair 0, 1 corresponds to 1, and the pair 1, 0 corresponds now to a variable Y. Okay, so so LH now corresponds to the following R module. So it's an R module before, it'll still be an R module now, and I'll call it I. This is now Y plus HR plus Q. Okay, so what I've done is what we've done is taken this basis, this 1 plus H, 1 comma H, and that corresponds to Y plus H, and likewise 0Q still corresponds to Q. So this is an R module, but it now lives in S instead of. Okay, so here are some facts. Fact 1 is that I is actually an ideal of S. This is an easy thing to check. You just check that y plus h times y still lives in I. Okay, and I can write the equations, but they're not particularly hard or insightful, so we just do that. So I is an ideal of S. And furthermore, an even more obvious thing is that f times y plus g lives in I. Okay, this is even follows directly from this conclusion. Okay, so it seems like we're in pretty good shape. We've gotten now, we've turned this lattice L sub h into an ideal of S. And moreover, that ideal contains the vector that we're looking for, the element that we're looking for. Okay. However, okay, however, I is not principal. Okay, I is not principal. Since we want to find fg or fy plus g, that's what we're looking for. Let's consider sorry. Well, typically it will not be principal. Typically, okay. So we'll see why not. I'm sure you can come up with pathological. Fy plus g to be generated. Yeah, right. That's more important. Yes. Okay. So typically not principal, and even if it were, fy plus g, typically it doesn't generate it. Could be. Yeah. So you're happy with any short vector in LH. Now, I think there are pretty reliable experiments that say this is basically a unique short vector up to these simple rotations. So multiplication by r in both coordinates, the same element on both coordinates. So no, I don't think so. I don't think so. Oh, yeah, but 1 plus x is in R. So I'm saying take any R multiple of this pair. It depends a lot on the. Sure, but for typical Q and typical FGs, right, this is sort of a unique short vector in the intervals, I think. Sure. Right. Enter sign, then you have a basis and so forth. Right. But in entering crypt is where you have this very short FG thing. So okay, I mean, this isn't the point. So I'll be glad to concede the point. But what we do want to investigate is this. We're going to consider I prime, which is generated by f plus g. Okay, so this is a principal ideal by definition. It's generated by fy plus g. So this obviously has yes. This ideal here. Okay, so the strategy is, and I'll now be able to write down the strategy or some observations about it of why it's useful. Yeah, this ideal here. Right, exactly. So we don't know this ideal. Here are some things we know about it, but we don't know this ideal exactly. So some facts. Well, the first is that I prime is a subideal of I, right? Simply because fy plus g is lived in I. So that's a subideal. Let's see. Its index is at most n to the n, probably something like that. Yeah. So we'll investigate that question actually. The second fact is that the generator Fy plus G, well, it might be, it is, or it might be short. Okay, short enough in the sense that, short enough that if you had an SGPIP oracle, it might return this generator, or up to some symmetries. Okay, so this is something that's plausible. I think you have to check it because we're talking about short in the canonical embedding, right? And y embeds as the square root of r and plus minus square root of r, which is moderately short. So there are things that have to be checked here, but let's suppose that this is the case. And so what this does is it gives us a strategy for how we might go after this. So the attack strategy. So let me define. So J will be the ideal that is the ratio I prime times I inverse. Okay. So J is the ratio of this ideal I prime that we care about to the ideal I that we have. So given the ideal I, what we'll do is just try many candidate J's. Okay, ideals J in S. Okay, run our SGPIP algorithm on I times J. Either gives us an answer or it doesn't, whatever it is. But when we get the right for the correct J, we get hopefully get Fy plus G, and then we've got our secret. Yes. So many candidates. So which candidates J should we be considering? All right. So candidate J. Candidate J means ideal of, well, it's going to have some norm, some bounded norm. Okay, accounting for this ratio, right? There's going to be some ratio between these, which is the true J. And so it's ideal bounded norm and in the inverse class of I. Okay, so it'll be in, how to write the notation here, but so I has a, in the class group of S, okay, what do we know is that I prime is principal. So we know that I prime is principal, and we have I, and supposing we knew the class group of S, then we should only be looking at J's which are in the inverse class of I, right? Because we want IJ to be principal. So these are ideals of norm B in the inverse class of I. Okay. Does that make sense? Yes. Well, that's the question. That's the important question, I think. So first of all, what is the proper norm bound to use here? And then, well, me too. Okay, good. So so we can see that. You can do experiments and such to find that out. So let me just, how big is the class group? Good. Okay. So there are two issues that really are basically problems to think about, questions to address. Okay. The first is, what is norm of J? Okay, because we're going to have to try ideals of norm up to about that large. Experimentally, In fact, norm of J tends to be very close around n to the n. Okay. And the second is how big is the class group of S? Okay, and that tells you roughly how many ideals you have to try here. Okay. So what you can do, well, we know something about the class group of R because R is cyclotomic. So pretty tight asymptotics on that. And I can show you my work and you can check it, but I think we get a crude lower bound of something like 39n to the n over 4, something like this, candidate J's. Okay, assuming that if this is your right norm bound, then just using the class group of R, you could show that there are at least this many candidate J's that you would have to try. If you can improve on this bound, then it'll cut down this proportionately. Yes. Maybe, yeah, I don't know. So to enumerate J's of all norms up to B, yeah. Right. What's our lattice here? Okay. I inverse, I think. Sorry. Mhm. Yeah.
You just sample in the reviews and calculate
Right. Okay. If it's a multiple, then you win. Yeah. Right. So, okay, I mean, that's a random sampling, which it's not clear if it corresponds to the enumeration. I'm not sure, but it could, yeah. Short UV. You're picking short UVs. Okay. So this is something that's going on. Let me conclude in 5 minutes by giving maybe an alternative view of what's happening, or trying to shed some other light on this. Oh, but I didn't put the second question here. If we don't get I prime exactly, okay. Right. Do you mean, so principal, right. Elements of I, okay. Product is principal, right. Mod units. Right. I think so, but yeah. Maybe that can help. I'm not sure. So I mean, there's all kinds of. This is just a template, and you can imagine lots of variations among it. Choosing an element of I and looking at the principal ideal it generates. Yes, yeah, and then hoping it's the secret key or related to the secret key. Right. So let me say an overall issue I think that one has to deal with here is whether I and I prime are actually related in any meaningful way, because maybe they are, maybe they aren't. It seems like there's some, it's unclear. Right. Okay. So just take another view at this, and then I'll wrap up. So another view, let's try to bring everything back to R. Okay, so bring everything back to R via the relative norm. Okay. So the norm S on R of I prime, we can write this out explicitly. It's F root R plus G, negative F root R plus G, that's G squared minus R F squared, okay? And then the norm, same norm, S on R of I, this is the QR almost always. This is something you can check. And so therefore, the norm of S on R of this factor J is merely G squared minus R F squared divided by Q. Okay. And so this, let's call this element W for wraparound. Okay. So if you look at, remember that R is congruent to H squared modulo Q, right? And H equals G divided by F mod Q. Those are the main relations. So if you just take, so G squared minus R F squared is indeed always divisible by Q. So you get from these relations, just pull the F over here and then substitute H squared with R. So that's what you get. So here is suggest an alternative attack. Which I think is strictly better, but there's one little qualification that one has to deal with. So the alternative attack is as follows. Instead of enumerating J's, okay, let's just enumerate the norm of J, the relative norm of J. So just enumerate candidate W's, okay, and then check when, check if you have the correct one. So how do you check a candidate W? So over here, to check for the right J, we multiplied I times J. We invoked the PIP, SGPIP oracle, and then we got an answer which we could check. So here, how do you check a candidate W? Make sure you're still awake. Check W times Q keep going, mod R is short. Okay, so yeah, if this is the right W, then W times Q is G squared minus RF squared. When you mod by R, you just end up with G squared. That'll be relatively short. And you can mod by R because R has these big coefficients that are random between Q and minus Q over 2 and Q over 2. So you'll get the right, G, or you'll get G squared. It'll be equal to G squared. Okay, so this I would say is doing almost the same thing as here, but there's one gap, which is that here we're trying only those J's in the inverse class of I, okay? And here we're trying all small W's, so candidate small W's. Okay, so there's a question that arises here. The enumerations of J versus of W might differ in a factor of the relative class number of S versus R. Okay, so class number of S, class number of R. Okay, so a question, interesting question is, what do the relative class numbers look like of this sort of, you have a cyclotomic here, and then you take this sort of random quadratic extension of it. Do we have any idea what happens to the class numbers? I have no idea. Does anybody have an idea? Heuristically, what you would even expect? Play the Jeopardy music for him. Okay, so we can ask later, but if this ratio is small, then the number of W's you're checking is essentially no worse than the number of J's you're checking here, and then checking is much faster here. So that's something you can see. Okay, and then I'll leave it as an exercise to come up with an alternative attack that doesn't use squaring at all. So we can avoid squaring as well, and probably cut down on the enumeration. So it's 12:30 now. So. All right. So if you want to know more, I'll hang around. Thanks. The bottom line of ring LWE. Oh, good. Okay, so you can probably do a similar setup with ring LWE. Maybe you need a cubic extension of R, something like this, or maybe it only has, it's not clear. But entry seems easier to, at least for a start, to attack, or to try to attack with these techniques. And if you make it work, you go to ring LWE after that.